Hi everyone, I am Dr.S.SURYA, Assistant Professor of Chemistry, A.D.M.COLLEGE for Women, Autonomous, Nagapattinam. Today we are going to learn about molecular spectroscopy for first semester chemistry. The rotational and Raman spectroscopy. The introduction to rotational spectroscopy. The rotational spectroscopy is a branch of molecular spectroscopy that deals with the study of rotational transition in molecules. It provides valuable information about molecular structure, moment of inertia, and bond length. The rotational spectrum of diatomic molecules, the energy level of rotational energy, are typically treated as a rigid rotator in rotational spectroscopy. The rotational energy levels are given by Ej is equal to Bj, J plus 1, Ej equal to Bj, J plus 1. So, Ej equal to Bj, J plus 1. That triple J is the rotational quantum number and triple B is the rotational constant. Explain how the energy levels are spaced and how they depend on the molecule's moment of inertia. The selection rule of rotational spectroscopy, the rotational transition are gone by selection rules. Therefore, minus del J is equal to plus or minus 1. Then minus del Mj is equal to 0. Then J equal to 0. Del Mj is equal to 0. Where Mjm and Jmj is the projection of triple J along the molecular axis. Discuss why these rules are important for the observing spectral lines and how they contribute to the structure of the rotational spectrum. The rotational spectrum describe the component of rotational spectrum: Q branch, P branch, and R branch. Q branch is explained about del J is equal to 0. That means del J is equal to 0 if transition lines are at the bond origin. Then P branch equal to del J is equal to plus 1. That means del J is equal to plus 1 transition is a higher energy level. Then R branch is equal to del J is equal to minus 1. That means del J is equal to minus 1, lower energy line. Then how the position and intensity of these branches related to the molecular rotational constant. The experimental technique, the overview of experimental method used in rotational spectroscopy such as microwave spectroscopy for low frequency transition and Raman spectroscopy for higher frequency transition. The principles behind these technique and their application in studying molecular rotation. The molecular parameter determination, how to rotation spectroscopy is used to determine molecular parameter like bond length, moment of inertia, and rotational constant. The applications of rotational spectroscopy in chemistry of determination of molecules in structure and reaction dynamics. In physics, study of molecular rotation and quantum effect. The rotational spectroscopy of polyatomic molecule. The rotational spectroscopy involved the study of rotational transition in molecules. For polyatomic molecule, rotational spectra provide information about molecular structure, moment of inertia, and internal dynamics. The rotational energy levels of polyatomic rotator, unlike diatomic molecule, polyatomic molecule have more complex rotational energy level due to their asymmetry and multiple axes of rotation. The rotational energy level are characterized by three rotational constants: AAA, BB, and CCC, corresponding to rotation around the principal axis of inertia. Next topic, the selection rule for rotational spectroscopy. The transition in polyatomic molecules depend on the molecular symmetry and rotational constant. Transitions are generally allowed to if they satisfy changes in triple J and triple K values, respecting the symmetry of the molecules. The rigid rotator approximation as rigid rotator for rotational spectroscopic analysis. The spectral lines are observed corresponding to rotational transition involving changes in triple J and triple K quantum numbers. The experimental technique for microwave spectroscopy and infrared spectroscopy. Microwave spectroscopy used for lower frequency transition, suitable for observing rotational transition in polyatomic molecules. And infrared spectroscopy for higher frequency transition, especially for symmetry molecules with stronger dipole moment. Technique involve exiting molecule to higher rotational state and measuring the resulting radiation absorption or emission. The molecular parameter determination, the rotational constant AAA, BB, and CCC, and moment of inertia and structural parameter. The rotational constant of AAA, BB, and CCC is from the spacing of rotational lines in the spectrum, providing information about molecular shape and moment of inertia. The moment of inertia derived from rotational constant and used to calculate bond length and predict molecular structure. Then structure parameter determined using the spectroscopic data in conjunction with the theoretical models to refined molecular geometry. Then application, structural illustration, atmospheric science, biochemistry. The structural illustration for molecular structure and conformation analysis based on rotational constant. Then atmospheric science, study of atmospheric molecule and pollutant using rotational spectra for identification and monitoring. Then biochemistry, analysis of biomolecules and their structural changes in solution using rotational spectroscopy technique. Then advanced topic in research in current, the centrifugal distortion and high resolution spectroscopy and polyatomic dynamics. The centrifugal distortion is deviation from the rigid rotator model due to molecular asymmetry or vibration rotation coupling. The high resolution spectroscopy advances in instrumentation allowing for precise measurement of rotational transition. Then polyatomic dynamics, understanding the molecular motion and interaction through rotational spectroscopy in complex systems. The intensity of rotational spectral lines. The intensity of the spectral line in rotational spectroscopy depends on various factors related to the population of rotation energy level and the quantum mechanical property of molecule. Then population of rotational energy levels, the Boltzmann distribution. At the thermal equilibrium, the population Njn and Jnj of rotational level J is given by the Boltzmann distribution. That means Nj is equal to N0. The intensity factor, the transit dipole moment. The intensity of spectral lines is proportional to the square of the transit dipole moment. The transit dipole moment quantifies the molecule ability to absorb or emit electromagnetic radiation during the rotational transition. It totally depends on the spatial orientation and electronic structure of the molecule. The selection rule of intensity factor, the intensity of the rotational transition is also influenced by the selection rule. For dielectric dipole transition in symmetric top molecules, del G is equal to plus or minus 1 and 1 del G is equal to plus or minus 1 and del K is equal to 0. So, these rules govern by which transition are allowed for forbidden based on the symmetry and quantum numbers J and K. The factors affect the intensity, temperature, pressure broadening and isotopic substitution. Temperature is a higher temperature lead to broader population distribution across rotational level affecting the intensity distribution of the spectral line. Then pressure broadening at higher pressure, collisional interaction can burden spectral lines and affect the intensity of profiles. Then isotopic substitution, different isotopes have different rotational constant affecting the intensity and position of spectral lines. Then application of implication, the quantitative analysis, astrophysical application and chemical kinetics. In quantitative analysis for intensity measurement can be used to determine the concentration of molecules and steady reaction kinetics. Astrophysical application, intensity variation in rotational spectra to help identify the molecule in space and steady physical condition in astronomical environment. Then chemical kinetics intensity measurement provide insight into reaction mechanism and dynamics involving rotational transition. The non-rigid rotator, introduction to non-rigid rotator. The rigid rotator assume constant bond length and angles during the rotation. Then non-rigid rotator consider molecules where bond length and angle change during rotation. Then molecular dynamics, the non-rigid rotator involve molecule with internal degree of freedom, for example bending and stretching vibration. The rotational energy levels are affected by these internal motions. The energy levels, vibration rotation interaction and Coriolis interaction. Vibration rotation reaction energy level are coupled due to vibration and rotational motions. Then Coriolis interaction, coupling between different vibration levels due to the rotation. The spectroscopic signature, the Raman spectroscopy and infrared spectroscopy. Raman spectroscopy, vibration modes affected by the rotation, giving rise to additional spectral features. The infrared spectroscopy, changes in vibration energies due to rotational motion. Then experimental observation, line broadening and isotopic effect. The line broadening explained in non-rigid rotator show border spectral lines due to multiple rotational vibrational transition. The isotopic effect in non-rigid rotator, in different isotopes may exhibit different non-rigid behavior due to mass differences. The non-rigid rotator in rotational spectroscopy, The peak shift changes in rotational constant and intensity due to coupling with vibration energy levels. The experimental observation in microwave spectroscopy, non-rigid effects are observed in molecule with a flexible bond. Example, CH2. The high resolution spectroscopy detailed in analysis of rotational transition affected by vibrational coupling. Non-rigid rotator in Raman spectroscopy, the vibration rotational coupling, spectroscopic signature, experimental observation and temperature effect. In vibration rotational coupling in non-rigid rotator exhibit coupling between vibrational and rotational modes affecting Raman spectra. Changes in molecular geometry during rotation alter the vibrational frequency observed in Raman spectra. The spectroscopic signature in isotopic shift in non-rigid rotator effect may differ significantly for different isotopic substituents due to changes in mass and vibrational coupling. The intensity changes in vibrational modes influenced by rotational motion may exhibit altered intensity in Raman spectra. In experimental observation, depolarization ratios. That means non-rigid rotator may exhibit changes in depolarization ratio compared to rigid rotator due to altered symmetry of vibrational modes. Then temperature effect in non-rigid rotator in Raman spectroscopy, temperature dependent changes in Raman spectra due to variation in molecular geometry and vibrational rotational coupling. Then classical theory of the Raman effect introduction. The Raman effect discovered by Sir P.V. Raman in 1928. In elastic scattering of light by molecule, incident photon interact with the molecule and are scattered at different frequencies. The mechanism of classical theory, incident photon interact with the molecule causing temporary polarization of the molecule. Molecule oscillate with this introduced dipole moment. Scattered photon frequency depends on the molecular vibrational mode. Then Stokes and anti-Stokes line. The Stokes line explained lower energy, that means longer wavelength. Scattered photon energy loss correspond to the energy of the molecular vibration. Then anti-Stokes line, that means higher energy or shorter wavelength. Scattered photon energy gain correspond to the energy of the molecular vibration. The polarizability of the molecule changes during vibration. Oscillating polarizability causes scattered photon at different frequencies. Then selection rule, the Raman active vibration change polarizability during vibration. Intensity of Raman scattering depend on symmetry and change in polarizability. Depolarization ratio of intensity of scattered light with perpendicular and parallel polarization in incident light. It provides information about molecular symmetry and orientation. Then classical versus quantum description. The classical theory describe only for Raman scattering based on induced dipole and polarization changes during vibration. Then quantum treats molecule and photons as quantized entities and explaining energy transfer between vibration and electromagnetic state. Then polarizability tensor, the basic concept polarizability is a measure of how much of the molecule electron cloud is distorted in response to an external electric field. In the smallest case where the molecular system is isotropic and the electric field is applied in a single direction, polarizability can be represented as a scalar. Then tensor formulation, in anisotropic or more complex molecular system, the polarizability is better described by a tensor. This accounts for the fact that the response of the molecule to an electric field can vary depending on the direction of the field related to the molecular structure. Then polarizability tensor is alpha is a second rank tensor that can be represented in a matrix form related to the induced dipole moment in the molecule to the applied electric field. That means Pi is equal to J, sigma alpha Ij is equal to Ij into Ej. The component of the tensor depend on the molecular structure and symmetry. For a molecule with a specific symmetry, the tensor can often be simplified due to the symmetry elements of the molecule. The polarizability ellipsoid concept. Ellipsoid are the geometric representation of the anisotropic polarizability of the molecule. They provide a visual way to understand how a molecule electron cloud responds differently to an electric field applied in different directions. The ellipsoid representation, the polarizability ellipsoid is defined by the polarizability tensor for a given molecule. This tensor can be diagnosed to find the principal axis and the corresponding polar stability. The ellipsoid is characterized by three principal axes, each corresponding to one of the principal polar stability. These axes represent the direction along with the polar stability of a molecule is maximum, intermediate and minimum. Then mathematical formulation, if you consider an ellipsoid with a semi-axis AAA, BBB and CCC, where AAA, BBB and CCC are the principal polar stability, then the ellipsoid can be described by the equation x squared plus b squared y squared plus c squared into z squared equal to 1. In this equation, x, y, z coordinate along the principal axis of the ellipsoid, and A, B, C are the length of the axis representing the principal polar stability of the molecule. Then interpretation of the shape and orientation of the polar stability, ellipsoid give insight into the anisotropy of a molecule responds to an electric field. If the ellipsoid is spherical, it indicates isotropic polar stability, meaning the molecule responds equally to an electric field in all directions. In ellipsoid with a different length for its semi-axis indicate anisotropic polar stability, reflecting how the molecular electron cloud is distorted differently in various directions. Application in Raman spectroscopy. In Raman spectroscopy, the interaction of light with the polar stability ellipsoid of a molecule provide information about vibrational mode. The intensity of Raman scattering depends on the change in polar stability along the different principal axes of the ellipsoid. The vibrational motion that cause significant changes in the ellipsoid shape for orientation lead to stronger Raman signal. Then symmetric consideration for molecule with specific symmetry in polar stability ellipsoid can be simplified or aligned with the molecular axis. The simplification helps in analysis and interpreting Raman spectra. Then molecular dynamics, the polar stability ellipsoid is also useful in understanding how molecular dynamics affect light scattering. Changes in the ellipsoid during molecular vibration influence the Raman scattering profile. The basis of the Raman effect, the monochromatic light scattered by the substance has component at different frequency from the incident light. This effect is due to the inelastic scattering of photon, meaning the scattered photon have different energy compared to the incident photon. The quantum theory, the molecular vibration and rotation, molecules have quantized vibrational and rotation energy level. When a molecule absorbs a photon, it can transition to a higher vibrational or rotational state. The scattering process, inelastic scattering, occurs when the molecule absorbs a photon, then re-emit it, but it not necessarily with the same energy. The different energy corresponds to the energy of vibrational or rotational transition. The interaction between light and a molecule is described by perturbation theory. The electric field of the light induces a dipole moment in the molecule, which causes transition between different energy levels. The polar stability tensor in Raman effect is related to the changes in polar stability tensor, the alpha and the of the molecule. The polar stability tensor described how the molecular electron cloud distorted in the response to the electric field. Then transition moment in Raman scattering intensity is proportional to the square of the change in polar stability tensor during the vibrational transition. The Raman scattering process, the instant photon with the energy IEE and IEI interact with the molecule. The virtual state, the molecule may temporarily enter in the virtual energy state, which is the not real energy level, but rather the transition state during the scattering process. The energy transfer of the scattered photon can have an energy that different from EIE and IEI. The energy difference correspond to the energy of the vibrational or rotational transition. Then Raman scattering type, Stokes scattering. The scattered photon has lower energy than the incident photon, indicating that the molecule has gained the energy. That means excited to the higher vibrational or rotational state. Anti-Stokes scattering, the scattered photon has higher energy than the incident photon, indicating that the molecule has lost the energy. That means de-excited from the higher vibrational or rotational state. And Raman intensity, the selection rule, the intensity of Raman scattering is proportional to the square of the change in the polarity tensor. That depends on the vibrational mode displacement and how much the polarity tensor changes during the vibration. The selection rule, not all vibrational mode contribute to the Raman effect. The change in polarity must be non-zero for a mode to be Raman active. The symmetry of the molecule and the vibrational mode determine whether it will be Raman active or not. The rotation energy level. The linear molecule, for example, CO2, NO2. For a linear molecule, the rotation energy level are quantized and described by the rotational quantum number. J, where J is a non-negative integer. The rotation energy level are given by Ej is equal to Planck constant. Then where is the moment of energy about this axis perpendicular to the molecular axis. In the rotational spectrum, the selection rule del G is equal to plus or minus 1, meaning that only transition between adjacent rotation energy level are allowed. Then Raman scattering in spectra, polarity tensor for linear molecule, the Raman scattering is influenced by the changes in polarity tensor due to rotational transition. The Raman intensity is influenced by how the polarity tensor vary with rotation. The Stokes line are absorbed when the scattered light with a lower energy or longer wavelength compared to the incident light. This occurs because the molecule absorbs the energy from the incident photon and transition to the higher vibrational or rotational state. The incident photon energy EIE equal to and EI interact with the molecule. The energy absorption energy from the photon causing into the transition from lower vibrational state to the higher vibrational state. The scattered photon, the molecule then re-emit the photon lower energy state with the correspond to the difference energy between the two vibrational states. The energy difference between the incident and the scattered photon correspond to the vibrational or rotation energy difference del E is equal to EI minus ES. This energy difference equals to the energy of the vibrational or rotational transition. The characteristic of Stokes line, the frequency shift. Del V is equal to EI minus ESH, where H is the Planck constant. The intensity of the Stokes line can be influenced by the population of the vibration level. Higher intensity is often absorbed in lower temperature samples because more molecules are in the lower energy state. The anti-Stokes line are absorbed when the scattered light has a higher energy compared to the incident light. This occurs because the molecule loses the energy due to the scattered photon, transiting from the higher vibrational or rotational state to the lower state. The incident photon energy EIE and IEI interact with the molecule. The energy emission initially in higher vibrational or rotational state loses the energy to the photon, transiting to the lower state. Then scattered photon has higher energy corresponding to the difference in energy between the two vibrational states. The energy difference between the incident and scattered photon corresponding to the vibrational transition del is equal to AS minus EI. Both Stokes and anti-Stokes line provide valuable information about the vibration and rotational state of the molecule and are used to study molecular structure and dynamics. The relative intensity of these lines can also provide insight into the temperature and population of different energy level in the sample. Thank you.